For more videos like this for discrete 1, you can take a look at Sarai's studies. Link is in the description box below. So far, we have studied the relationship between sets, which is what we did in this video. But now we're going to study the relationship between elements, and there's two ways we can go with this. We can either study the relationship between elements in the same sets or the relationship between elements in different sets. For example, let's say I have a set containing the elements 1, 2, 3, and 4. I can study the relationship between elements in this set. So maybe I can see how 1 is related to 2, or 1 is related to 3. Or if I have this set A that contains mom, friend, daughter, I can see how mom is related to friend, or if mom is related to daughter. Or I can study the relationship between elements in different sets. So I can have two different sets A and B, and I can study how maybe 1 is related to 4 or 2 is related to 3. So the relationship between elements in different sets. Now to figure out which elements are related in a set, we need to list out all possible relationships between the elements in that set. In other words, we need to list out all possible combinations of the elements in that set. So how can we do this? Well, there's this tool that we learned in the last lesson. It's called the Cartesian product. If you take the Cartesian product of a set with itself, that actually is going to give you the set of all possible combinations of all of the elements in that set. However, if you take the Cartesian product of a set with another set, it gives you all possible combinations of the elements in both sets, but with the restriction that if you have this combination, A always comes from set A and B always comes from set B. But again, when you take the product of a set with itself, it's actually all the combinations of the elements in a set. So let's take this set, for example, that contains the elements mom, friend, and daughter. If I want to list out all possible relationships or combinations of the elements in the set, I'm going to take the Cartesian product of the set with itself. So I'm going to need double the set. So I have this set, I'm going to take double it. And the rule is always take the first set that they give you, go to it. In this case, they're both the same, so just pick one, doesn't matter. And the idea is that for every element in the set, you're going to pair it with every element in the other set. So the Cartesian product is going to be the set of mom with mom, mom with friend, mom with daughter. You're done with this one, you move on to the next. Then you pair friend with mom, friend with friend, then friend with daughter, then you move on to the next, daughter with mom, daughter with friend, daughter with daughter. So this is actually all the possible relationships or all possible combinations of the elements in this set that you can have. So out of all of these possible relationships, your relation is actually going to be the set of all the relationships that satisfy the relationship that your professor wants to be satisfied, and they'll describe the pairs, the relationships that they want you to extract and put in your set by using set builder notation. So they'll say, okay, your relation is going to be the set of all ordered pairs such that, and the first thing is that the ordered pair should come from this set. So you're going to say that ordered pair is going to be an element of this set of A times A, the Cartesian product of the set with itself. Now Garcia doesn't write this part because it's implied that every pair in the relation comes from this set, but formally it's there. And then anything after that, your professor can just make up. Like, this is the rule that they want you to satisfy. So let's say the rule is that A cannot be the same as B. So remember that every pair here is A comma B. So in this case, this pair would not be in this relation because A is literally the same as B. They're both the same. And maybe the second rule is that A is blood related to B. So let's pretend that there's no adoption in this world. So your relation R is going to be equal to the set of all of these relationships where A is not the same as B. So already I know it's not going to be this one because they're the same. It's not going to be this one because friend and friend are the same. And it's not going to be this one because daughter and daughter are the same. And the second rule is that A is blood related to B. So I already know it's not going to be mom and friend because a mom and a friend are not blood related. I know it's going to be mom-daughter because mom and a daughter are blood related. It's not going to be a friend and a mom. It's not going to be a friend and a daughter because a friend and a daughter are not blood related. It is going to be daughter and a mom because, again, daughter and mom are blood related. It's not going to be a daughter and a friend, and that's it. So at the end of the day, your relation is going to contain only the pairs that satisfy this rule here, this relationship that your professor wants you to satisfy. So it's going to contain only this one, mom, daughter, and daughter, mom. So it may be helpful to always remember this analogy of using people as the elements of a set, because you can remember that this is all possible relationships, and then your relation is all actual relationships given whatever rule your professor gives, or again, whatever relationship your professor wants you to satisfy, because that relationship might not even make sense. It might not actually be a relationship that you would see in real life. For example, instead of the relation actually being those who are literally related to each other, for all you know, they could have said where the ordered pair is equal to friend comma mom. So then the only pair, the only relationship in your relation would just be this pair. That would be the only one in here because that's what the rule says. So it's all actual relationships that satisfy the relationship that they they want you to satisfy, that your professor is always going to give you. Let me do one more example that will transition us to the next video. Let's try this set now. So I'm going to find the Cartesian product of that set with itself. So I'm going to have one copy of the set and another copy of the set. Rule is you take the first one that they gave you, go to it. In this case, it could be this one or this one, doesn't matter. But the idea is pick one, and for every element in that set, you're going to pair it with every element in the other set. So the Cartesian product is going to be equal to the set of 1 paired with 1, of 1 paired with 2, 1 paired with 3, 1 paired with 4. Then you move on to the next. 2 paired with 1, 2 paired with 2, 2 paired with 3, and 2 paired with 4. Then you move on to the next. 3 paired with 1, 3 paired with 2, 3 paired with 3, 3 paired with 4. Then you move on to the next. 4 paired with 1, 4 paired with 2, 4 paired with 3, and 4 paired with 4. So these are all of the possible relationships, all of the possible relations. But let's say your professor this time says your relation is going to be the set of ordered pairs such that that ordered pair comes from this set, so A times A, and A is equal to 1. So you're only going to pick ordered pairs from the set where the first value is 1. So that's this one, and this one, and this one. So your relation is going to be the set of these pairs, of these A, B coordinate pairs. So that's the idea. Here your professor gives you the description of your set. It says it has to be made up of these ordered pairs, and it is made up of these ordered pairs, such that these pairs come from this set, and that the first value is 1, which they are. They're all 1. So at the end of the day, a relation is a subset of the Cartesian product of a set with another set. But in this class, Garcia only teaches this section, so it's just going to be Cartesian product of a set with itself. And we don't say proper subset because it could be equal. It could be that the relation is made up of all of these pairs. Now, for some notation, we say that 1 is related to 2, 1 is related to 3, 1 is related to 4, and here 1 is related to 1. Now, where do we go from here? Well, the idea is we have these sets called relations. First topic of discussion is what are the different ways to represent this set, this relation? Well, there's 3 ways: roster notation, which is what you see here, matrix notation, and a directed graph. Second topic we're going to cover is the idea that relations have properties. They could be reflexive, irreflexive, symmetric, antisymmetric, transitive, and we're going to work on identifying if a relation satisfies those properties by just looking at roster notation, or just by looking at a matrix, or just by looking at a directed graph, and so on. But first we're going to practice how to read set builder notation and how to know which points, which pairs to extract and put in our relation given a certain rule, whatever relationship your professor wants you to satisfy. So let's get started. So here we have a set A, its elements are 1, 2, 3, and 4, and we have the Cartesian product of A, which contains all of the possible combination of all of the elements in A with all of the elements in A. Now I want to start with this one because it's the easiest, but just to note, in all of these relations, the ordered pairs should come from the Cartesian product of A with itself. In other words, if I read this, it says that the relation is going to be made up of all of the ordered pairs A and B such that A is not equal to B. But what I didn't write because there's no space is another condition, which is this one, that the ordered pair that's going to end up in this relation should come from one of these, right, from the Cartesian product of A with itself. So really this should be R is equal to the set of all ordered pairs A and B such that this condition, the ordered pair, comes from this set, A times A, and then A is not equal to B. And that's true for all of these relations. This relation is going to be equal to the set of all ordered pairs where A is not equal to B. So you just go here and pick the ones where A is not the same as B. In other words, it's going to be every pair except 1, 1, 2, 2, 3, 3, and 4, 4. Other than that, A is not the same as B. So this is going to be equal to the set of 1, 2, 1, 3, 1, 4, 2, 1, 2, 3, 2, 4, 3, 2, 3, 4, 4, 1, 4, 2, and 4, 3. So every single one of these except these ones. Now let's try this one. So here a relation is going to be equal to all ordered pairs from this Cartesian product from this set such that A is less than B. So let's go through each one. Is A less than B? No, 1 is not less than 1, so we're not including this one. Is 1 less than 2? Yes, so we're including this one. Is 1 less than 3? Yes, so we're including that one. Is 1 less than 4? Yes. Is 2 less than 1? No. Is 2 less than 2? No. Is 2 less than 3? Yes. Is 2 less than 4? Yes. Is 3 less than 1? No. Is 3 less than 2? No. Is 3 less than 3? No. Is 3 less than 4? Yes. Is 4 less than 1? No. Is 4 less less than 2? No. Is 4 less than 3? No. Is 4 less than 4? No. So the only ones we're including in our relation are the circled ones. So I'm going to go in order. That's 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and finally 3, 4. Let's try this one here. Our relation is going to be equal to the set of all ordered pairs that are in this set where A divides B, meaning no remainder. So for the first one, this is A, this is B. Does 1 divide 1? Yes. This is A, this is B, so B is 2. Does A divide B? So does 1 divide 2? Yes. And we know that 1 divides everything, so all of these are true. This is A, this is B. Does 2 divide 1? No. This is A, this is B. Does 2 divide 2? Yes. This is A, this is B. Does 2 divide 3? No. This is A, this is B. Does 2 divide 4? Yes. This is A, this is B. Does 3 divide 1? No. This is A, this is B. Does 3 divide 2? No. This is A, this is B. Does 3 divide 3? Yes. This is A, this is B. Does 3 divide 4? No. This is A, this is B. Does 4 divide 1? No. This is A, this is B. Does 4 divide 2? No. This is A, this is B. Does 4 divide 3? No. This is A, this is B. Does 4 divide 4? Yes. So only the ones circled are going to go into this set. So I'm going to go in order. We first have 1, 1, then 1, 2, then 1, 3, then 1, 4, then 2, 2, then 2, 4, then 3, 3, then 4, 4. And that is our set. Here, relation is going to be made up of all of the ordered pairs that are in this set such that B is equal to A squared. So let's go through it. For this one, this is A, this is B. If I square A, am I going to get B? Yes. 1 squared gives me 1. If I square this, do I get 2? No. If I square this, do I get 3? No. If I square this, do I get 4? No. If I square this, do I get 1? No. If I square this, do I get 2? No. If I square this, do I get 3? No. If I square 2, do I get 4? Yes. If I square this, do I get 1? No. If I square this, do I get 2? No. If I square this, do I get 3? No. If I square this, do I get 4? No. If I square this, do I get 1? No. If I square 4, do I get 2? No. If I square 4, do I get 3? No. If I square 4, do I get 4? No. So our set, our relation is going to be equal to only 1, 1, and 2, 4. These are the only ordered pairs from this set that satisfy this relation. And finally, this set is going to contain all of the ordered pairs that are in this set such that A minus B is an even number. So let's start with the first one. This is A, this is B. Is A minus B even? Well, is 1 minus 1 even? Well, 0 is even. Remember that the definition of an even number S is that you have some integer K. If you multiply by 2, you get S. So if 0 is even, then 2 times some integer must give me 0, and it could be that that integer is 0, so yes, 0 is even. 1 minus 2, that's negative 1, is that even? No. 1 minus 3, that's negative 2, is that even? Yes. 1 minus 4, that's negative 3, is that even? No. 2 minus 1, that's 1, is that even? No. 2 minus 2, that's 0, is that even? Yes. 2 minus 3, that's negative 1, is that even? No. 2 minus 4, that's negative 2, is that even? Yes. 3 minus 1, that's 2. Is that even? Yes. 3 minus 2, that's 1. Is that even? No. 3 minus 3, that's 0. Is that even? Yes. 3 minus 4, that's negative 1. Is that even? No. 4 minus 1, that's 3. Is that even? No. 4 minus 2, that's 2. Is that even? Yes. 4 minus 3, that's 1. Is that even? No. 4 minus 4, that's 0. Is that even? Yes. So this relation is going to be equal to the set of all of the ones circled. So that's 1, 1, 1, 3, 2, 2, 2, 4, 3, 1, 3, 3, 4, 2, and 4, 4. Now these are relations. We can represent relations two other ways. This is roster notation. We can also represent relations with the matrix and with a graph. Now when you're working with the matrix, you need some indices to represent the rows and to represent the columns. Your indices are going to be all of the elements in your original set. So that's 1, 2, 3, 4, and 1, 2, 3, 4. So you make your little matrix, and then looking at this relation, this is the way you read it. 1 is related to 1. So 1 is related to 1, so you write a 1 if they are indeed related. 1 is related to 2. So 1 is related to 2. So you put a 1. So notice how this is the first number, this is the second number. You go by row and then by column. Then we have 1 is related to 3. So 1 is related to 3. So there's a 1 here. Then you have 1 is related to 4. 1 is related to 4. So 1 here. Then you have 2 is related to 2. So 2 is related to 2. So there's a 1 here. Then you have 2 is related to 4. So 2 is related to 4. So there's a 1 there. 3 is related to 3. So 3 is related to 3, so there's a 1 here. And then 4 is related to 4. So 4 is related to 4. So right here, there's a 1. And then everywhere else, you just put a 0. So 0, 0, 0, 0, 0, 0, 0, 0. Let's try this one. So I'm just going to copy this little template and erase everything on the inside. So again, 1 is related to 2. So 1 is related to 2. So over here, there's a 1. 1 is related to 3. So 1 is related to 3. So over here, there's a 1. 1 is related to 4. 1 is related to 4. So over here, there's a 1. 2 is related to 3. 2 is related to 3. So over here, there's a 1. 2 is related to 4. 2 is related to 4. So over here, there's a 1. 3 is related to 4. Forgot a little parenthesis here. 3 is related to 4. So over here, there's a 1. And then everywhere else, there's a 0. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Now let's try the next one. I'm just going to make a little copy for each of these. Here we have 1 is connected to 1, so 1 is connected to 1. There's a 1 there. Then 2 is connected to 4, so 2 is going to be connected to 4, so over here there's going to be a 1. And everywhere else there's going to be a 0. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. 1 is related to 1. So 1 is related to 1, you put a 1 there. 1 is related to 3, 1 is related to 3, so 1 goes here. 2 is related to 2, 2 is related to 2, so 1 goes here. 2 is related to 4, so 2 is related to 4, so a 1 goes there. 3 is related to 1, 3 is related to 1, so a 1 goes here. 3 is related to 3, 3 is related to 3, so a 1 goes there. 4 is related to 2, 4 is related to 2, so 1 goes there. And finally, 4 is related to 4, 4 is related to 4, so 1 goes here. And everywhere else, there is a 0. For this one, we have 1 is related to 2, so 1 is related to 2, a 1's going to go here. Then we have 1's related to 3, so 1 is related to 3, a 1's going to go there. Then we have 1 is related to 4, so 1's related to 4, a 1's going to go here. Then we have 2 is related to 1, so 2 is related to 1, so 1's going to go there. Then we have 2 is related to 3, 2 is related to 3, so 1's going to go there. Then we have 2 is related to 4, 2 is related to 4, so 1's going to go here. Then we have 3 is related to 1, so 3 and 1, a 1 goes there. And we have 3 is related to 2, so 3 is related to 2, a 1 goes there. 3 is related to 4, 3 is related to 4, a 1 goes here. 4 is related to 1, so 4 is related to 1, a 1 goes there. 4 is related to 2, 4 is related to 2, so 1 goes there. 4 is related to 3, 4 is related to 3, so 1 goes here. And everywhere else is just zeros. The third way you can represent relations is with a directed graph. So you're just going to take your indices, or all of the elements in your original set, and you're going to make a dot for each of them. So 1, 2, 3, and that's going to be the same for every single one of these, because all of these relations are from the same set, this one here. Now you can go from roster to this, or you can go from matrix to this. I always like looking at the matrix. So by looking at the set itself, you could say there's an arrow from 1 to 1, or in other words, 1 is connected to 1. So you do a little loop-de-loop. Or you can use the matrix and say there's an arrow that goes from 1 to 1. So 1 really means arrow. Here we have there's an arrow that goes from 1 to 2. So from 1 all the way to 2. You can read it as there's an arrow from 1 to 2. Here there's an arrow from 1 to 3. So from 1 to 3 there's an arrow from 1 to 3. Here there's an arrow from 1 to 4. So an arrow from 1 to 4. There's another arrow from 2 to 2. So we just have an arrow pointing back to 2. Here there's an arrow from 2 to 4. So we go from 2 to 4. There's another arrow from 3 to 3. So we have an arrow going from 3 back to 3. And finally we have an arrow going from 4 to 4. So we have an arrow going from 4 back to 4. And we call this a directed graph or a digraph because the arrows are directed. It's not like 1 and 4 are connected this way. There's an arrow that says, okay, we're going from 1 to 4. There's a distinction. Now let's find the graphical representation of this relation. Again, you can read it from roster notation. There's an arrow from 1 to 2. Or you can look at the matrix and say, oh, there's a 1. That means arrow. There's an arrow from 1 to 2. So we draw an arrow from 1 to 2. There's an arrow from 1 to 3. So you see another 1. Oh, there's an arrow from 1 to 3. So you do an arrow starting from 1 all the way to 3. There's an arrow from 1 to 4. You see a 1. There's an arrow from 1 to 4. So we do an arrow from 1 all the way to 4. I see another 1. That means there's an arrow from 2 to 3. So again, whatever representation of the relation you want to use to get to another, it's up to you. I see another 1. That means there's an arrow from 2 to 4. So from 2 all the way to 4. I see another 1. That means there's an arrow from 3 to 4. So 1 from 3 all the way to 4. And that's your graph. Here I see a 1, that means there's an arrow from 1 to 1. That means there's an arrow coming from 1 back to 1. Here I see another 1, that means there's an arrow from 2 to 4. There's an arrow from 2 to 4, so I go from 2 all the way to 4. For this relation, I see a 1, that means there's an arrow from 1 to 1. There's an arrow from 1 to 1, that means we have an arrow coming from 1 back to 1. I see another 1, that means there's an arrow from 1 to 3. So from 1 to 3, I go from 1 all the way to 3. I see another 1, that means there's an arrow from 2 to 2. So from 2 to 2, I go from 2 all the way back to 2. Then I see another 1, that means there's an arrow from 2 to 4. So from 2 to 4, I go from 2 all the way to 4. I see another 1, that means there's an arrow from 3 to 1. From 3 to 1, so I'm going to go from 3 back to 1. I see another 1, that means there's an arrow from 3 to 3. So from 3 to 3, that means I go from 3 all the way back to 3. I see another 1, that means there's an arrow from 4 to 2. So from 4 to 2, that means I go from 4 all the way back to 2. And then finally there's another 1, that means there's an arrow from 4 to 4. From 4 to 4, that means it goes from 4 all the way to 4. I see a 1, that means there's an arrow from 1 to 2. From 1 to 2, that means from 1 all the way to 2. I see another 1, that means there's an arrow from 1 to 3. So from 1 all the way to 3. I see another 1, that means there's an arrow from 1 to 4. So from 1 all the way to 4. I see another 1, that means there's an arrow from 2 to 1. So from 2 back to 1, there's an arrow. I see another 1, that means there's an arrow from 2 to 3. So from 2 all the way to 3, there's an arrow. Another 1 means there's an arrow from 2 to 4. I see another 1, that means there's an arrow from 3 to 1. So from 3 all the way to 1. I see another 1, that means there's an arrow from 3 to 2. From 3 all the way to 2. I see another 1, that means there's an arrow from 3 to 4. So from 3 all the way to 4. Another 1 means there's an arrow from 4 to 1. So from 4 all the way to 1. Another 1 means there's an arrow from 4 to 2. So from 4 all the way to 2. And finally another 1, that means there's an arrow from 4 to 3. So from 4 all the way to 3. So these are the 3 different ways we can represent relations: roster notation, matrix notation, or using a directed graph. Now the second topic of discussion is these relations have properties. R stands for reflexive, I stands for irreflexive, S stands for symmetric, A is for antisymmetric, and T is for transitive. So here are all of them spelled out, and the reason why they are teaching you the different ways to represent a relation is because sometimes one representation is easier to use than another to tell if that relation satisfies a certain one of these properties. So I'm going to tell you right now, the easiest default way is use a matrix for these 4. And then for the transitive, use the roster notation. I'll teach you the algo to follow, but sometimes it's more apparent with the graph. But it just depends on whatever you want. I use the matrix for everything but the transitive one. So is this relation reflexive? Well, reflexive just means you have all ones in the main diagonal, which you can see in the matrix, so yes, it is reflexive. But how to tell from roster notation? It just means that if you have an element A, then A comma A should exist in your set. So if I have an element 1, then 1 comma 1 should exist, so it's here. If I have an element 3, then 3 comma 3 exists, so it's here. If I have an element 4, then 4 comma 4 exists, so it's here. So this one tells me I have 1 1, this one tells me I have 2 2, this one tells me I have 3 3, this one tells me I have 4 4. If you're looking at a graph, if you see loops on all of your little dots, then you know it's reflexive. So if you see all loops, reflexive. If you see all ones in the main diagonal, reflexive. If you see twins, reflexive. What about this relation? Is it reflexive? Well, I don't see ones in the main diagonal, so it's not reflexive. I don't see loops in every single dot, so it's not reflexive. I don't see any twins in the roster notation, so it's not reflexive. For this relation, I don't see ones in the main diagonal, so it's not reflexive. By the way, main diagonal means this. The other diagonal would be this one, just in case you forgot some vocab from linear algebra. Is this relation reflexive? Well, I see all ones in the main diagonal, so yes. In the graph, I see loops on every single dot, so yes. In roster notation, I see twins for every single element in the main. Let me highlight these as well. Is this relation reflexive? Well, I don't see ones in the main diagonal, so no. I don't see loops in every single dot, so no. I don't see all of the twins that I need to in roster notation, so no. Is this relation irreflexive? Irreflexive means that you have all zeros in the main diagonal. We don't, so this is not irreflexive. Is this relation irreflexive? Well, we do have all zeros on the main diagonal, so it is irreflexive. In other words, it's the opposite of this one. It means we don't have twins. So if we have 1 in the original set, in the relation, we cannot have 1 1. We can't have twins. Graphically, it means that none of the little dots, none of the indices, none of the elements have loops. If at least one has loops, it's not irreflexive. If there's at least one twin in the roster notation, it's not irreflexive. If there's at least 1 1 here, it's not irreflexive. Is this relation irreflexive? Well, I don't see all zeros in the main diagonal. There's at least 1 1. There's at least 1 twin. There's at least 1 loop. So no. Is this relation irreflexive? Well, if it's reflexive, it's not going to be reflexive. So no, because I don't see all zeros on the main diagonal. I see at least 1 twin. I see at least 1 loop. So no. Is this relation irreflexive? Well, I see all zeros in the main diagonal, so yes it is. In roster notation, I don't see any twins. I don't see 1 1. I don't see 2 2. In graphical representation, I don't see any loops, so it is irreflexive. Now, is this relation symmetric? Easiest way, use the matrix. In linear algebra, we learned that if we have a matrix, let's call the matrix A, then if we take A transpose, that's just a fancy way of saying, hey, switch all of the rows with the columns. If the transpose ends up being the same as the original matrix, then it is symmetric. So for this matrix, I'm going to take this column, make it a row. I'm going to take this column, make it a row. I'm going to take this column 1, 0, 1, 0, make it a row. I'm going to take this column 1, 1, 0, 1, make it a row. Is this the same as this matrix? No. You can see that here we have 1, 0, 0, 0. Here we have 1, 1, 1, 1. It's not the same matrix, so it's not symmetric. What this really means, though, in roster notation, is if you have A comma B in your relation, then you will also need to have B comma A. Graphically, that means if you have an arrow from 1 to 3, then you will also have an arrow from 3 to 1. So think you need the opposite in order for it to be symmetric. But the easiest way is really to take the transpose of the matrix. So for this one, this matrix is going to be, I'm going to take this column, make it a row. Already I can stop here because I know that this matrix is not going to be the same as this one because this one has 0, 1, 1, 1 as its first row. Here we have 0, 0, 0, 0. So they're not going to be the same, so it's not symmetric. Graphically, I can see it's not symmetric because there's an arrow from 1 to 3, but there's not an arrow from 3 to 1. In order for it to be symmetric, if there's an arrow from 1, it has to go back. If there's an arrow from 1, it has to go back. Arrow from 1 has to go back. Arrow from 1, it has to go back. But that's not the case, so it's not symmetric. Is this relation symmetric? Well, just by looking at the roster notation, I can tell it's not, because there's an arrow from 2 to 4, but there's not one from 4 to 2. That's what it means. If you have 2 to 4, then you should have the opposite, and I don't. So I already know it's not symmetric. Another way is to look at the matrix, calculate the transpose. So in this case, I take the first column, and I make it a row, so it's 1, 0, 0, 0. I have the first row, let's move on. I take the second column, I make it a row, 0, 0, 0, 0. Already I know it's not going to be the same matrix because here there's a 1, here there's a 0, not the same matrix, so it's going to be a no. Graphically, I can tell it's not symmetric because there's an arrow from 2 to 4, yet there's not an arrow from 4 to 2. So no, symmetric doesn't mean that you have to have opposite arrows for every index. No, it just means if there is one from one point to another, then there should be one from that point to this one. There isn't, so it's not symmetric. Is this relation symmetric? Well, graphically, I see that there's one arrow from 1 to 3, and there's one from 3 to 1, and there's one arrow from 2 to 4, and there's one from 4 to 2. So when there's an arrow from one point to another, you have the opposite arrow. There's an arrow from one point to another, you have the opposite arrow, so it is symmetric. When there's too many elements, I don't even bother. I just go to the matrix, the transpose of this matrix, just switch the rows and columns. This column becomes a row, this column 0, 1, 0, 1 becomes a row, this column 1, 0, 1, 0 becomes a row, this column 0, 1, 0, 1 becomes a row. Is this matrix the same as this one? Yes, they're the exact same matrix, so because matrix A is the same as the transpose of matrix A, these are the same, then you can say that the relation is symmetric. Is this relation symmetric? Well, again, when there's too many elements, I don't even bother with roster notation. I just go to the matrix. So this is matrix A, let's say. So the transpose of A, just switch the rows and columns. So this column, 0, 1, 1, 1 becomes a row. Then we have 1, 0, 1, 1. Then we have 1, 1, 0, 1. Then we have 1, 1, 1, 0. The question is this matrix the same as this one? Yes, you can see that they're the same, so because of that, it is symmetric. Another way to look at it graphically is that if there's an arrow from one point to another, then you have the opposite arrow. An arrow from one point to another, you have the opposite arrow. An arrow from one point to another, you have the opposite. Arrow from one point to another, you have the opposite. Arrow from one point to another, you have the opposite. Arrow from one point to another, you have the opposite. So it is symmetric. With roster notation, if you see a point 1, 2, then you should see the opposite point 2, 1. But let's say that you didn't have these points, you didn't have these arrows, then it would still be a symmetric relation because the rule is if there is an arrow from one point to another, then you have to have the opposite arrow. But if there isn't that arrow, then you don't need the opposite arrow. So it's fine. It's still symmetric. So it has to be true for every single point. So if I see 1, 3, then I should also see 3, 1. But that doesn't mean that the whole relation is symmetric. I have to keep going. If I see 1, 4, then I should see 4, 1. If I see 2, 3, I should see 3, 2 right here. If I see 2, 4, then I should see 4, 2 right here. It's still not symmetric. If I see 3, 4, then I should see 4, 3. Now it's symmetric because for every pair I see the opposite one. So this should be true for all of the cases. I'm just not going to highlight everything green, but that's the idea, okay? Same thing here. This is like the whole thing is green. Because if I have 1, 1, I have 1, 1. If I have 1, 3, then I have 3, 1. If I have 2, 4, I have 4, 2. If I have 2, 2, I have 2, 2. If I have 4, 4, I have 4, 4. If I have 3, 3, I have 3, 3. So at the end of the day, everything's green, so it's symmetric. But I'm not going to highlight everything.
Now, is this relation antisymmetric?
That just means in a matrix is outside of the main diagonal, so you're going to ignore all of these ones. If you see a 1, then its opposite position, so if this is at 1, 3, and the opposite position is 3, 1, should be a 0. And that should be true for all of the ones you see outside of the main diagonal. If you find at least one where the opposite position is 1, then it's not antisymmetric. So I see a 1 here, its position is 1, 2. So the opposite position is 2, 1. So do I see a 0? Yes, I move on. Here I see another 1 outside of the main diagonal. Its position is 1, 3. Its opposite position is 3, 1. Do I see a 0? Yes. Here I see another 1 at 1, 4. Its opposite position is going to be 4, 1. Do I see a 0? Yes, so I move on. Here I see a 1. Its position is 2, 4. So the opposite position is 4, 2. Do I see a 0? Yes. So because for every one outside of the main diagonal, there's a 0 in their opposite positions, then this relation is antisymmetric. So it's just the ones that matter, not the zeros. You don't care about the zeros. Is this relation antisymmetric? Well, outside of the main diagonal, I have to check every one. So here there's a 1 at 1, 2. So the opposite position is 2, 1. Do I see a 0 here? Yes, I move on. Here's another one. It's at 1, 3. Its opposite position is going to be 3, 1. Do I see a 0 here? Yes. Here I see another one. It's at 1, 4. Its opposite position is 4, 1. Do I see a 0 at this corner? Yes. Here I see another one. Its position is 2, 3. Its opposite position is 3, 2. Do I see a 0 at this corner? Yes. Here I see another one. Its position is 2, 4. So opposite position is 4, 2. Do I see a 0? Yes. Here I see another one. It's at 3, 4. Opposite is 4, 3. Do I see a 0 at this corner? Yes. So because for every one outside of the main diagonal, there's a 0 in its opposite position, this is antisymmetric. So check. Again, outside of the main diagonal, if I see a 1 and I see a 1 at 2, 4, then the opposite position for 2, I should see a 0. Is that true? Yes. Since that's the only one, then that's the only one you have to check, so it is antisymmetric. Again, outside of the main diagonal, if there's a 1, there is a 1 at 1, 3, then opposite is 3, 1. Is there a 0 at this corner? There isn't. There's a 1. This should be a 0. So because we found a case where it's not 0, it's not antisymmetric. Again, outside of the main diagonal, for every 1, there should be a 0 on the opposite side. But notice, there's only 1s here. So there's never going to be a 0 anywhere here. So I already know that it's not antisymmetric. I could check. For 1, 2, I have a 1. So the opposite would be 2, 1. Do I have a 0 in this corner? No. It should be 0. All of these should be 0 because all of these are 1s. And that's not the case. So it's not antisymmetric. So in conclusion, a relation being antisymmetric means if there's an arrow from 2 to 4, then there's not going to be an arrow from 4 to 2. In other words, there's an arrow from 2 to 4, there's no opposite arrow. If there's at least one opposite arrow, the whole thing is not antisymmetric. And the last property is transitive. How do we know if a relation is transitive? The way I remember is T for triangle. So just imagine a triangle. The whole idea is if you have a point that goes from A to B, so you have a point that goes A to B, and you also have a point that goes from B to C, so you have a point that goes from B to C, then there should be a point that goes directly from A all the way to C. In other words, from A all the way to C, there should be A to C. That's what a transitive property is. And if there isn't that point, if there isn't an arrow that goes from A to C, that shortcut, if this is the situation, then the whole relation is not transitive. Graphically, we can tell if there's a point from 1 to 2, and then there's a point from 2 to 4, then there should be a point from 1 to 4. That's what transitive means, and there is from 1 to 4. But if you have a lot of points, it's really hard to keep track. I mean, yeah, it's kind of easy to tell, but like you'll lose track with these two methods. So I just kind of follow a little algorithm, and I'll show you how to do it with roster notation. So instead of thinking it from a triangle perspective, let's think about it from a linear perspective. If you have a point A comma B, and then you have a point B comma C, then the transitive property says that you have to have a point A, C. In other words, looking at roster notation, if you find a point, you're searching for any other point that has the same B value, and then you have to make sure that AC exists. In other words, this is my first point. The B value is 1. So I'm searching for every other point that has this 1 as its A value, as its first value. So it's this one, and this one. So if we look at these ones first, this is A, this is B, this is C, then there should be AC. So there should be 1, 2 in the relation. Is there 1, 2 in the relation? Yes, there is. But that doesn't mean it's transitive. You have to also check this one. Is there 1, 3 in the relation? Yes, there is. You also have to check this one. Is there 1, 4 in the relation? Yes, there is. And you would have to continue the same pattern for all of the points in this relation. And when you have a lot of points in the relation, it's going to get a little bit hard to keep track of which points you've checked and which you haven't. So I'm going to show you what I call my little table method to help you keep organized when checking if a relation is transitive. So for this first relation, I'm just going to grab it and drag it all the way down here. So for each of these points, you're going to have a row. So for 1, 1, you're going to have a row. For 1, 2, you're going to have a row. 1, 3, you're going to have a row, and so on. And then you're going to have a column. And here's how this algorithm works. You're going to start with your first point. Remember that it's A comma B, so A is 1, B is 1. You want to focus on your B value. Your B value is 1. So you're going to go through all of the points, including the one that you're looking at. And the ones you're going to add here are those that start with your B value. So you're just looking for those that start with 1. So this one starts with 1, so you're going to add 1, 1 here. This one starts with 1, so you're going to add 1, 2 there. This one starts with 1, so you're going to add 1, 3 there. This one starts with 1, so you're going to add 1, 4 there. The rest of them do not start with 1, so you're good. Remember that the whole idea is if you have a point A comma B and a point B comma C, then the transitive property says you have to have a point going from A to C. So same B values, all of these have the same B values. So you're just going to be checking for each of these points if there's a point from A to C in your relation. So here's how it's going to go. Same B value. Is there a point 1, 1? Yes, there is. Is there a point 1, 2? Yes, there is. Is there a point 1, 3 in your relation? Yes, there is. Is there a point 1, 4? Yes, there is. Done with this point here. You move on to the next one. This is your B value. You're going to look at all of your points. So you want points that start with 2. So this one and this one. So you're going to add 0.22 here and 2, 4. Same algorithm. Look at your outskirt value. So is there a 0.12? Yes, there is. Or 0.14? Yes, is your next point. This is your B value. You're looking at all of them. Start with 3. Only this one starts with 3, so that's the one you're going to put here. Then you say, is there a 0.13? You're just looking at your outskirt values. Yeah, 1, 3 is right here, so you're done with this one. 1, 4, B value is 4. You're going to look at all of them. Write the ones that start with 4. Only this one starts with 4, so you're going to put it here. Is there a 0.14? You're done with this one. B value is 2. Look at all of them. Which ones start with 2? This one and this one. So you're going to add this one here and this one here. Then you do the algorithm. Is there a 0.22? Yes, there is. Is there a 0.24? Yes, there is. Move on. For this one, B is 4. Look at all of them. Which ones start with 4? Only this one. So you're going to write this one there. Is there a 0.24? Yes, there is. So you're done with this one. B value is 3. Which one of these start with a 3? Only this one. So you're just going to write it there. Is there a 0.33? Yes, there is. Then for this one, B value is 4. Which one out of all of these start with 4? Only this one. So you're going to write it here. Is there a 0.44? Yes, there is. So the whole idea is when we had a point A comma B and B comma C, there was always an A comma C. An A comma C. So because that's true for every single point that we just checked, this relation is transitive. So over here, there's a check mark. For your second relation, again, you're going to have a row for each of these points. So 1 for 1, 2, 1 for 1, 3, 1 for 1, 4, and so on. Then you're going to have a column, and all you're going to put in here depends on what your B value is. So for this first one, B value is 2. So you're just going to look at all of them, including the one you're looking at right now, and see which ones start with 2. So that's this one and this one. So 2, 3 is going to go here and 2, 4 is going to go here. Then you want to look at the outskirt numbers. So the ones on the outside. So 1 with 3. You ask yourself, is there a 1, 3 in your relation? Is there a 1, 3 here? Yes. You're done with this one. Is there a 1, 4? Yes. So that's good. You're done with all of them in the row. So you're done with this coordinate. Moving on to the next. There's a 3 here. Do you see any coordinates that start with 3? Yes, this one. So this is going to go here. Then you ask yourself, look at the outskirt values. Is there a 1, 4 in this relation? Yes, there is. You're done with everything in the row. Move on to the next. Here you have a 4. Do you have any points that start with 4? No. So by default, it's a check. For this one, there's a 3. Do you have any points that start with 3? Yes, this one. So that's the point you're going to put in here. Then look at the outskirt values. Is there a 0.24? Yes, there is. You're done checking all of the points in this row, so you're done with this point. Moving on to the next one. Here we have 4. Are there any points that start with 4? No. So by default, it's a check. Here we have 4. Are there any points that start with 4? No. So by default, it's a check. When you have all checks for every single point in your relation, that means that your whole relation is transitive. So if we go back up here, I'm going to do a little check for this one. Is the third relation transitive? Again, you want to make a row for each one of the points that you have. So 1 for 1, 1, 1 for 2, 4, then your little column. The points that are going to go here for this specific row are ones that start with 1. Do you have any points in this little column here that start with 1? Yeah, this one. So you're going to write it there. Then again, you look at the outskirt numbers, the ones on the outside. So is 0.11 in your relation? You're going to look at all of the points here. Is there 1 here? Yes, there is. Because you checked all of the points in this row, you're done with this row. Moving on to the next. The points that are going to go here are the ones that start with 4. Do you have any points here? Any points in your relation that start with 4? No, so there's nothing there. So by default, it's a check. Because you have all checks for all of the points that you have in your relation, it is transitive. So if we go back up here, we're going to do a little check for the third relation. Now is the fourth relation transitive. Again, for every point you want to have a row, so we're going to have a row for 1, 1, for 1, 3, for 2, 2, and so on. We're going to make this a column. Now the points that are going to go here are ones that start with 1. So out of all of the points in your relation, this one starts with 1, this one starts with 1, and that's it. So you're going to put 1, 1, and 1, 3. And then remember, you're looking at the outermost values. So with this one and this one, this is the outer one, this is the outer one. Connect them to each other. Ask yourself, do you see the point 1, 1 in this relation? Yes, I see it right here. So done. Then for this one and this one, outermost point, outermost point. Do you see a point 1, 3 in this relation? Yes, I do. So because I'm done going through all of the points in this row, I'm done with this one. And move on to the next. The points that are going to go here are the ones that start with 3. Out of all of these, this one starts with 3, this one starts with 3. So 3, 1's going to go here, and 3, 3 is also going to go there. Then again, is 0.11 in this relation? Yes. Is 0.13 in this relation? Yes. I'm done with all of the points in this row, so I'm done with this point here. Moving on to the next. Points that are going to go over here are ones that start with 2. Out of all of these, this one starts with 2, this one starts with 2. So 2, 2 is going to go here, and 2, 4 is going to go there. Same pattern. Is 2, 2 a point in this relation? Yes. Is 2, 4 a point? Yes. I'm done with all the points in this row, so I'm done with this point. Moving on to the next. The points that are going to go here start with 4. Out of all of these, which ones start with 4? This one and this one. So 4, 2 is going to go here, and 4, 4 is going to go there. Again, is 0.22 in this relation? Yes. Is 0.24 in this relation? Yes. I'm done with all the points in this row. I'm done with this point. Moving on to the next. The points that are going to go here start with 1. Out of all of these, which ones start with 1? This one and this one. So 1, 1's going to go here, and 1, 3 is going to go there. Again, is the 0.31 in this relation? Yes. Is the 0.33 in this relation? Yes. I'm done with all of the points in this row, so I'm done with this point. Moving on, all the points that are going to go in this row start with 3. Out of all of these, which ones start with 3? This one and this one. So it's going to be 3, 1, and 3, 3. Then again, is 3, 1 in this relation? Yes. Is 3, 3 a point in this relation? Yes. I'm done with all of the points in this row, so I'm done with this point. Move on to the next. All the points that are going to go here start with 2. Out of all of these, which ones start with 2? This one and this one. So 2, 2 is going to be a point, and 2, 4 is going to be a point. Is 4, 2 a point in this relation? Yes. Is 4, 4 a point in this relation? Yes. I'm done with all of the points in this row, so I'm done with this point. Moving on to the next. All the points that are going to go here start with 4. Out of all of these, which ones start with 4? This one and this one. So 4, 2 is going to go here, 4, 4 is going to go here, and then again, same pattern. Is 4, 2 a point in this relation? Do I see 4, 2 here? Yes. Is 4, 4 a point in this relation? Do I see 4, 4 here? Yes. I'm done with all of the points in this row, so I'm done with this point. Because all of them are check marks, this relation is transitive. Again, you want to make a row for every single point in your relation. So 1 row for 1, 2, 1 for 1, 3, 1 for 1, 4, and so on. Make this a column. And then the points that are going to go in this first row are those that start with 2. So out of all of these, which ones start with 2? This one, and this one. So 2, 1's going to go here, 2, 3 is going to go here, and 2, 4 is going to go here. So for this first point, you ask yourself, is 1, 1 in this relation? Well, out of all of these points, do you see 1, 1? No, 1, 1 is not in this relation. So therefore, you don't even have to check the other 2 points. As soon as you get a no, the whole thing is no. As soon as you see an X, the whole thing is not transitive. So you could have check mark, check mark, check mark, check mark, X. As soon as you get an X, the whole thing is not transitive. If we go up here, relation 5 is not transitive. So to conclude, if your relation is reflexive, it has all 1s in the main diagonal. If it's irreflexive, it has all 0s in the main diagonal. If it's symmetric, it just means that your matrix, if we call every matrix A, like this is matrix A, this is matrix